you all for showing up. How many of you know what a Sphero is? So we're going to show you some pictures in a minute, but it's a little plastic robot, basically. You can buy them online, and we did our project on, well, probably best to show you what it is first.
There we go.
All right, well, I'm Daniel Tobin.
I'm Melissa, and our project was collision detection with Sphero.
That's an older.
What is Sphero? Sphero is, well, that is what Sphero looks like. He is a little spherical robot that fits in the palm of your hand. And when you cut him in half and take out his innards, that's the inside right here. He has two wheels that allow him to move forward and around in a circle. And he also connects to a mobile device using Bluetooth.
It has two sensors inside of it. One is a gyroscope and one is an accelerometer. The gyroscope is mainly used to keep the internals balanced, and that's used to also move it around. And the accelerometer, how many of you know what an accelerometer is? So an accelerometer very simply measures acceleration. As an example, if you're driving in your car and you accelerate to 25 miles per hour, you're going to measure some sort of acceleration. Once you reach 25 miles per hour and you're no longer changing your speed, you're no longer accelerating. So if you had an accelerometer, it would read 0. Inside the Sphero has 3 accelerometers, one that measures forward and backwards acceleration, one that moves side to side acceleration, one that measures vertical up and down acceleration. And for our project, we are measuring forward and backwards and the side to side acceleration.
Our project objectives were to stream live data from Sphero's accelerometer to our mobile device, see if we can take that data to detect collisions from there, filter the data to see if we can find some indications that we maybe be able to create a formula to actually just run in the background, automatically detect it, and then from there calculate at what angle Sphero collided with something like a wall. How we approach the problem, we first decided to design a mobile application using Android and Java. What this application did, it would tell Sphero to roll forward, and then you can tell it to stop, and then it would create a text file, everything the accelerometer read. From there,
So what would happen is it would roll forward and collide with a wall. Now, what the accelerometer data would show is that as it's rolling forward, we would see a slight acceleration as it's moving from a stop to a speed. Once it's at that speed, it's going to stay. The acceleration is not going to be anything notable. Once it collides with the wall, it's going to be a very fast deceleration. So then the accelerometer will read some values that would indicate that there is a collision.
Alright, and then from there, we'll show you in a little while how we actually computed everything. We put it into Excel, looked at some graphs and how the graphs were looking. We see a wonderful peak when it hit the wall. And then from there, we took the X and Y values at the collision to determine what angle it hit. And then from there, we modified the application to do it at runtime, so you don't have, so it just, you ran Sphero and it would say whether it collided with a wall or not.
Real quick, I wanted to explain the reason we wanted to do this. Robotics has this sort of, as a field, has this sort of challenge of how does a robot analyze the world? Robots might be able to do it with a camera to look around. They could do it with a GPS to determine their location. The Sphero has neither of those. It has an accelerometer and a gyroscope. So we wanted to design this application to sort of give the Sphero a better idea of what is going on around the world. So, if the Sphero didn't have this code running, it would run into a wall. It wouldn't have any idea what angle it hit the wall. It doesn't have any idea what the world around it looks like. So by designing this application to tell Sphero what angle it hits a wall at, we can sort of give the robot an idea of what the world looks like, so it can just make decisions on its own about what to do. So, you know, if it collides with a wall, it says, okay, well, there's a wall there. I'm not going to try and keep driving into that wall. I'm going to try and move in a different direction. So that was the reason why we did this.
And here are some snapshots of what our application actually looked like on Dan's Android phone. We have the way to create the file name, adjust Sphero's speed, because you can do that, change the direction that you want Sphero to go in, and then hit go for it to go on forward, and then stop. And then we have a calculate angle button, which will tell you, as you can see in some of the other examples, what angle it hit. These examples hit about at an 80-degree angle, so close to 90 degrees, but not quite. This isn't going to copy this. Alright, so let's get back into the math of how this actually works. This is a graph of unfiltered data straight from Sphero's accelerometer. As you can tell, it's very jittery, very difficult to read and see what's happening. And so what we did was we filtered the data using a median filter, and it's so much easier to read and decide, okay, at this big peak right in the center, that's where the Sphero collided with a wall.
And we should mention that the x-axis is time in seconds. So you can see at the very left, that's 2.14 seconds into the test run. So right at the peak, you can see about 2.62. That's at the time it collided with a wall, because there's a large spike in acceleration at that time.
Okay. And from there, we decided to look for peaks, which again signify that a collision had actually occurred. And from there, after a series of runs, we were able to determine that there was a threshold that would determine if a collision had happened and if it did not. And that was at about 1 g, which is in gravity. Alright. And here's some different sample runs at 135 and 45 degrees.
The orange line on the top is the x value, so that would be, if you imagine the Sphero facing forward, x would be left and right, and the yellow would be the y value, which would be, if the Sphero is facing forward, it would be simply forward and backwards.
Right. In order to calculate the angles, we took the filter data and we looked for the peaks, and since this is a 45-degree angle, there were 2 of them at approximately 2 seconds into the run trial. And from there, we did some magic finding the arctangent of y over x, and it came out to be about a 52-degree angle. And then from there, we implemented that logic into our application to do it during runtime.
And this is just some information. In conclusion, we decided that if the accelerometers read any value above 1, then that would have been that would signify that a collision had occurred. And from there, we developed an algorithm basically to determine what the angle of collision was. Oh yeah. So we had a couple other ideas for further research. If you guys know what a Roomba is, it's those little vacuum cleaner robots that run around a room, and when they hit a wall, they'll turn in a different direction and move. We sort of thought that the Sphero could do the same sort of thing, but almost more accurately, because the Sphero the Roomba can't tell, you know, if it hits a wall at a slight angle, or if it hits it straight on, or at another sort of angle. The Sphero would be able to tell what angle that wall was at, so it could essentially map a room or map a maze based on its collisions with walls. And do you want to describe the conclusion?
And further, you can take this away from Sphero, but use the same logic in vehicle collisions. Every car is equipped with several accelerometers in there, and so it